Okay, so we're going to do some practice questions on waves, and we're going to start with waves in the electromagnetic spectrum. So which one of these three wave properties is the same in a vacuum for both X-rays and radio waves? That is the speed at which they travel. It would be 3 times 10 to the 8 meters per second. Which of these determines the color of a ray of light? Color corresponds to wavelength. That our eyes essentially measure the wavelength of light, and that gives us color. Which of these is the distance between two successive wave crests? That is also wavelength. Which region of the electromagnetic spectrum has the shortest wavelength? That is our gamma rays. They have the shortest wavelength or the highest frequency. Okay, so observations of a distant thunderstorm are made. During a lightning flash, the average wavelength of the light emitted is 5 times 10 to the minus 7 meters. This light travels at 3 times 10 to the 8 meters per second. Calculate the average frequency of this light. So we're just going to use the wave equation. We're going to rearrange that to make frequency the subject, plug the numbers in, and we get the frequency 6 times 10 to the 14 hertz. The interval between a lightning flash being seen and thunder being heard is 3.6 seconds. The speed of sound in air is 340 meters per second. Calculate the distance between the thunderstorm and the observer. So, the equation we're going to use is the average speed is distance divided by time. As long as the speed is constant, we can use this to calculate speed as well. So distance is speed times time, so therefore we get 1224 meters or 1.2 kilometers. Explain why the speed of light is not taken into account in this calculation. Well, because it would only take 4.1 microseconds for the light to travel 1.2 kilometers, so it's just completely insignificant because it's so much faster than sound. And if you want to know how I got the 4.1 microseconds, I just did 1.2 kilometers divided by 3 times 10 to the 8, and you realize how short the period of time is, and that's why we ignore it. Okay, so a single ray of white light from the lightning is incident on a prism as shown. Complete the path of the ray to show how a spectrum is formed on the screen. Label the colors. So essentially what happens is at the first boundary you get the dispersion of the wavelengths. Red is refracted the least, violet is refracted the most, or violet travels closest to the normal. Whichever you like to phrase it, you end up with this kind of split, and all the other colors would be in order in between. Okay, so the diagram shows the air pressure variation along a sound wave. So on AB, mark one point of compression with a dot and a C, and the next point of rarefaction with a dot and a letter R. So a compression would be where the air pressure is slightly higher. The next rarefaction would be at the trough down here, where the pressure is actually the lowest. In terms of the wavelength, what is the distance along the wave between a compression and the next rarefaction? Well, compression to compression would be one wavelength, so compression to rarefaction is half a wavelength. A sound wave travels in air at a speed of 340 meters per second. Calculate the frequency of a sound wave of wavelength 1.3 meters. So this is our equation. We rearrange to make frequency the subject, and then we give it to an appropriate number of significant figures. Fairly straightforward. In a thunderstorm, both light and sound waves are generated at the same time. How fast does the light travel towards an observer? Well, it's 3 times 10 to the 8 meters per second. Explain why the sound waves always reach the observer after the light waves. Well, sound travels at 330 meters per second in air, so that's about 1,000,000 times slower than light, which is 3 times 10 to the 8. So that's why. Speed of sound waves in air may be determined by an experiment using a source that generates light waves and sound waves at the same time. Draw a label diagram of the arrangement of a pseudo apparatus for the experiment. Well, essentially, I think a very good visual and sound things would be a pair of cymbals. So all you need to do is get an observer or a timer a certain distance away, and they measure the time difference between seeing and hearing. So state the readings you take. So you measure the time difference between seeing the cymbals clash and hearing the sound, and measure the distance between the cymbals and the person doing the timing. And using those, you could get speed by doing distance over time. So explain how you'd calculate the speed. Well, you divide distance by the time, and that gives you the wave speed. So the diagram shows diffraction of waves by a narrow gap. P is a wavefront that has passed through the gap. Draw 3 more wavefronts to the right of the gap. So what we're looking for here is we get these semicircular wavefronts and that the wavelength is not affected by diffraction. So the distance between wavefronts should stay the same. The waves travel towards the gap at a speed of 3 times 10 to the 8 meters per second and have a frequency of 5 times 10 to the 14 hertz. Calculate the wavelength of these waves. So here's the wave equation, rearranged to make the wavelength the subject, plug the numbers in, and we get our wavelength 6 times 10 to the minus 7, which is very much in the visible spectrum. So the diagram shows an optical fiber. XY is a ray of light passing along the fiber. On the diagram, continue XY until it passes Z. So optical fibers work based on total internal reflection. So essentially what we should see is a series of reflections with the angle of incidence roughly equal to the angle of reflection. Explain why the ray does not leave the fiber at Y. So the angle of incidence must be greater than the critical angle, and light is travelling in a higher optical density material than the surroundings. So we've got the two conditions to have total internal reflection. The light in the optical fiber has a wavelength of 3.2 times 10 to the minus 7 and is travelling at a speed of 1.9 times 10 to the 8. Calculate the frequency of the light. So we're just using our wave equation, rearranged to make frequency the subject. That gives us a value. Speed of light in air is 3 times 10 to the 8. Calculate the refractive index of the material. So refractive index is speed of light in a vacuum divided by speed of light in a material. That comes out as 1.6. The diagram shows the path of a sound wave from a source X. State why a person standing at point Y hears an echo. Well, the sound wave reflects off of the wall, and you can see that they're in the right position because when the angle of incidence equals the angle of reflection, you can see the path will go straight through Y. The frequency of the sound wave is 400 Hertz. State the frequency of the sound wave reaching Y. Well, it's 400 Hertz. No process like reflection, refraction, whatever changes the frequency. Frequency is determined by the source of the waves. So it's going to be 400. The speed of a sound wave is 330. Calculate wavelength. So again, we're just using the wave equation, rearranged to make wavelength the subject, plug in our values, we get our answer. Sound waves are longitudinal waves. State what is meant by the term longitudinal. The wave causes the particles in the medium to oscillate parallel to the direction of energy transfer. In this question, drawing should be done carefully. The diagram shows a ray of light striking mirror 1 at point X. Draw the normal at X. Alright, there we go. Draw the ray reflected from mirror 1. So we should have the angle of incidence equal to the angle of reflection. Mark the angle of incidence with an I and the angle of reflection using the letter R. So there we go, they're always measured to the normal. Mirror 2 is parallel to mirror 1. The reflected ray from mirror 1 strikes mirror 2. Compare the direction of the ray reflected from mirror 2 with the incident ray at X. You may wish to construct, so that it's going to be parallel to the original ray. Because the mirrors are parallel, the ray will end up being parallel to the original one. The diagram shows an arrangement where a plane mirror is used in a shop to watch a display counter around a wall. The arrangement is drawn to a scale of 1 centimeter equals 1 meter. State the law of reflection. Well, angle of incidence equals angle of reflection. On the diagram, draw rays to show how much of the screen of the display cannot be seen from P. Indicate this by shading the part that can't be seen. Okay, so essentially I drew a ray from P to the very edge of the mirror and then applied angle of incidence equals angle of reflection, and anything beyond that they're not going to be able to see. So you can see I did it for the other end as well, but we can see that's not going to place a limitation on what you can see. So you can see that this part of the counter is not going to be able to be seen. So the next part of the question asks us to find how far we would need to move the mirror in order to see the rest of the counter. So here what I did is I drew a line from the extreme part of the display counter that when reflected went to P, and we can see that we're going to need to move the mirror by this distance, and from the diagram we can see that that distance is 1.7 centimeters, which means it's 1.7 meters in reality because of the scale used. State the characteristics of an image seen in the plane mirror. It should be the same size as the object, the same distance from the mirror as the object. It should be upright, but it will be laterally inverted, so its left and right will be switched. Speed of sound in air is 340. Complete the table to show how far the sound wave has travelled in 2, 3, 4 and 5 seconds. So essentially we just need to increase the number by 340 every second. Draw the graph of distance travelled against time for the sound wave. Alright, so let's plug those values in, so they should come out as a straight line, and we can put a line of best fit in as well. A ship is sinking in the dark, as shown in the diagram. The sailors on the ship fire a distress flare into the air. It explodes with a bang and a bright flash of light. The lifeboat crew hears the bang and sees the flash, but not at the same time. State which reaches the lifeboat first, and the bang of the flash, and give a reason. The flash, because light travels 1,000,000 times faster than sound does in air. It's 3 times 10 to the 8 to 3 times 10 to the 2. Time interval is 4.2 seconds. Use your graph to find out how far away the lifeboat is from the flare. Show clearly on your graph how you got your answer. So essentially what we need to do is draw a line up at 4.2, draw a line across, and we can see it's 1400 meters. An inventor is trying to make a device to enable him to see objects behind him. He cuts a square box in half, sticks 2 plane mirrors on the inside of the box. So we've got an arrangement here. Okay, so we've got it drawn in showing some angles now. So the diagram shows the light rays continue the 2 rays until they reach the place where the inventor's head will be. So we're going to have the first ray doing this, and we're going to have the second ray doing this. The angle of incidence is 45 degrees at both mirrors, so the angle of reflection should be 45 degrees at both mirrors. What can be said about the image the inventor sees? Well, it's going to be upside down. You can see the 2 rays have switched places. So a student wrote the following report about an experiment to measure the speed of sound in air. My friend and I went into a field a long way from any buildings and measured the distance across the field. My friend stood at one side of the field and I stood on the other. My friend banged 2 pieces of wood together, and as I saw him do this, I started the stopwatch. I stopped the stopwatch when I heard the sound, and we obtained the following readings. We've got distance and time. Why does it need to be a long way from buildings? Well, we need to prevent any echoes occurring which could interfere with our measurement. Why do we need a large distance? Well, we need a large enough time that it's going to be accurate. Say our time was going to be 0.1 seconds, timing that accurately is very difficult. If we're doing something close to a second, we can actually reasonably time that accurately. Suggest what the students could have used to measure the distance. A tape measure, a very long one, or a trundle wheel would also have worked. Why was there a delay between the students seeing the pieces of wood come together and hearing the bang? Well, as we've seen before, light travels 1,000,000 times faster than sound. Use the readings to calculate the speed of sound. So speed is distance over time, as long as the speed is the same the whole time. So it's 340, which seems very reasonable for sound. Suggest why it might have been a good idea for the students to repeat the experiment after they had exchanged positions, well, to check if their result was reliable, though you know it's reliable if you keep getting the same reading over and over again, and it would also allow them to calculate an average speed while having several sets of data. A narrow beam of red light strikes one face of a triangular prism, as shown. So what we're going to do is I'm going to draw on what would happen next, because that's almost certainly where this question is going. So we get it being refracted at both surfaces. Okay, so we've shown that. What name do we use to describe what happens to the beam at A? We call it refraction, the changing of direction due to a change in speed. So the red light is replaced by a beam of mixed red and violet as shown. So what we're going to get is something like this that we saw earlier. Red is not going to be refracted as much as violet, or violet is going to be closer to the normal than red. So the beam of red and violet light is replaced by a narrow beam of white light from the sun. State what is now seen on the screen. Well, you're going to see a full spectrum of visible light because it's been dispersed into its separate colours. The rays from the sun also include infrared. Infrared radiation can pass through glass. Mark with the letter X the place where you'd see the infrared radiation, so it would be refracted even less than red would, so you're going to see it on this side. Why can infrared not be seen? Well, it's not visible to the human eye. It's not part of the visible spectrum. What could be used to detect it? A thermometer would work, an infrared camera would also work, anything that allows you to see where infrared has arrived. We're going to see is going to be our virtual image. In the diagram, waves from a point source in a tank of water strike a straight barrier. The reflected wavefronts seem to come from a single point. On the diagram, mark a dot to show the position of this point, label that C. So the thing I'm going to do is I'm actually going to construct ray diagrams. Remember, rays always travel perpendicular to wavefronts. So that's what I've done. And I'm going to do another one as well. And just as before, I'm going to extrapolate the reflected ray back. And we can see that they converge at this point. And it should be no surprise, it's equal distant from the barrier as the source. And then what I'm going to do is I'm going to set up circular waves coming out of there with the same wavelength, and we end up with this diagram here, and we can see where the reflected rays would be. Okay, so that completes the set of questions looking at waves.